So today we are going to talk about database development lecture 13, the query processing, the query plan, and the execution. So the semi-join where the R1 semi-join R2 where we take the tuples from R1 matching the tuples from R2, which can be expressed by the following operator, where the module's semi-join lecture will be like we can firstly rename the modules to module prime in the lectures, and we do the Cartesian product from the modules and after the renamed lecture, and then we select where the module equals to the module prime, and we project them to only the module and years. So the thing is that we select so for the first thing, I'm not sure what is select one mean. Actually, I'm not sure what is select one, and the next thing is select all from modules. Yeah, it's R1. R1 is everything in the R1 is concluded, where it is matching the tuples in R2. Yeah. So why this one can, because we are selecting from the attributes where it's within R1's module. We are selecting R1's attributes. Yeah. And we are going to talk about the query processing. With the initial SQL plan, we can pass the query to the pre-process and the logical query plan, and we can optimize the logical query plan. To the optimized logical query plan, we can select the physical query plan, and we can do the physical query plan, do the query execution. The query processing is that the SQL query we can pass them, and in this lecture we're going to talk about the query plan, and the query plan is the relational algebra expression that is combined into an SQL query. So it is called logical query plan. Select the module name from module's lectures where code equals module and year equals 2. Yeah, this is the query plan for that. And this query plan can be represented as a tree, where we project the module and name, and where the code equals module and year equals 2, and we are just coming from this one. This is at the bottom, the Cartesian product, and then we do the selection and we do the projection. That is, and this exercise we can do represent the following query plan as a tree. And there are many different query plans. The database management system combines the best possible, where this one is identical to this one, but this one is more efficient since we are natural drawing fewer atoms. And the execution of the query plan is that the query plan tells us exactly how to compute the result. Usually it proceeds from the bottom to the top. We compute an intermediate result from each node, and each as the leaves associated with a relation R, and then we got the intermediate result of R. If the inner node is the intermediate result, for example, in this case, the module is here, and we remove code equals to module, and because we want to do the natural join where it must be common attributes, and the lecture is here, and we select the name and the module, and then we natural join them to module, year, and name, and we select them, and we are going to execute this query plan where we firstly select A and B, and in this case we select B to C and C to D, and we renaming them, and we do the Cartesian product. It is worth noticing that in the projection one, we are reducing the this one replicate. And another thing is about I think they are unique, right? And how to apply the operator is how to compute the select condition R. Is we can read through the whole file, or we can use the naive computation of the drawings, which is just for each tuple R, for each tuple S in S, if they have the common values, the output is natural drawing. But this is too slow, because it's just like anytime we in this case they are matching. And we are going to output them here. And however, if they are not matching, we are not output them. This the runtime is R times N, R times S. It's the number of tuples in R times the number of tuples in S. So can we do faster? Yes. So we have the equal join where the R equal join S is defined as select A equals to B, R times S, and if R is sorted in A and B is sorted, then the R equal join S can be computed as one pass through R equals to S. It's just like this is less than this. This is less than this. Then we are going to move further, and then we are computed the natural drawing. We get 1, and then we are when we keep on moving further. We get another one, which is here, and we keep on moving further. We get another one here, and then we keep on moving for this one, and we are moving further from this one. We get we are keep on moving further for this one, and we got this one, which is here, and therefore it is going through once, and it is much better. So however, the thing is that what if there are so many replicated duplicated things, then the effect is not very strong. For example, if it is 1 1 1 1 together with 1 1 1, then we are not replacing the pointer very quickly, and it's just it is just the original thing, which is R times S. So this is just to illustrate that. Therefore, the sort join algorithm, where we are going to compute the equal join R and S, where we first sorted on A and then we sorted on B. We merge the sorted R and S. The running time for a sort R on A is R times the number of operations in R times the log base 2 of the number of tuples in R. And the running time of the sort S on B is the big O of the number of tuples in S times the log base 2, the number of S, and then we merge the two sorted R and S. Total running time is R plus S. The actual running time is actually since it's the upper bound, where it is R times log base 2 of R plus S times log base 2 of S. And typically faster with the nested loop join. Typically faster than the nested with much faster. And as a remark, there are various of join algorithm. We have the hash join, index join, and mutual join. And other computations of the relational algebra, we neglect the relation. We have neglect that relation. We have neglect that relation that's stored in the disk. We did not consider the disk. We are just thinking about the memory access, not the disk access. And therefore, what if we are reading a relationship in R? It takes O of R, and since it is the number of the disk access that dominate the time for the operation. Therefore, we can see the B, which is the size of one disk block, and the size of one disk block times the number of disk access will be the number of tuples in R. Therefore, the M is equal to the number of disk blocks. Therefore, this is R. This is big O R divided by B. Sort algorithm in A, we should take R times base 2 of R, log base 2 of R. Then the reason why is that we can easily thinking that the number of disk iteration is just replacing the R to the R divided by B, and however the M is number of the disk blocks fits into a variable RAM. The number of disk blocks that fits into the RAM. Number of disk blocks that fits into the RAM. I'm not sure where this M is, and I'm going to clarify that. Okay, let's continue that. In summary, the query plan evaluated the bottom up from the leaf to the node, and each operator can be computed in different ways. For the selection, the linear scan. For the projection, we can also do the linear scan. For the join, we can do the nested join loop, sorted join, index join, hash join. In the next lecture, we're going to have a faster query plan with indexes. Thank you very much. Welcome commenting and subscriptions.